Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Resource allocation and, of course, selfish agents who are going to actually participate in the implementation of this allocation of resources. You are trying to organize the rules of the games in such a way that, following their selfish interest, I mean, they will arrive exactly where you want them to arrive. I mean, it's kind of a very generalized metaphor of the invisible hand. I mean, you try to put right there where you want the invisible hand in every circumstance, and when is it possible, when is it not? Now, in that tradition, the trend on which, for instance, I've been, sort of evolving in my own work since the mid-70s, which is about when I was born academically, and till now, till recently, was to look at the implementation problem as one of where you try to really reach your target exactly by adjusting the strategic analysis, and more specifically the equilibrium concept, to the particular goal you have in mind. So without, of course, trying to do an overview or anything, but what has happened is that, starting from the initial work in the mid-70s, where people were concerned by initial notions such as strategy proofness, I mean, very strong robustness of the mechanism in the form of dominant strategy of truthfully revealing your characteristics. And after realizing that this sort of condition was very stringent and imposed very, very severe limitations on the things you could achieve, then the whole literature has developed in which successively we looked at a number of different equilibrium concepts. Some of them, I mean, of course, starting with the well-known Nash equilibrium, but then going into a large number of variants and refinements and variations around this theme. So, I mean, that's an interesting route, but it runs the risk of, in some sense, exhausting itself by almost inventing a new equilibrium concept each time you have a new problem of a different difficulty, and then sort of making the conclusion much more difficult to evaluate. I mean, because when you don't know what is the robustness of the equilibrium concept you are looking, when you are obliged to make some strong informational assumptions and specific assumptions about the way coordination works or doesn't, and so forth, you are diminishing rapidly the strength of your conclusions. Now, here in this talk, I want to borrow this idea that came up recently, as you know, in the computer science literature. I mean, this term coined by Koutsoupias and Papadimitriou, which is a very simple, basic performance index called the price of anarchy, but which surprisingly, well, maybe not surprisingly, but we didn't think about before. I mean, when I discovered it recently, it sort of became obvious to me that there is a nice range of application of the idea in traditional microeconomic mechanism design, where we should try to follow these ideas, and that's what I'm starting to do here. Okay, so I'm not going to go over the history of that concept and the papers on congestion games by Roughgarden, Tardos, and so forth, because I think you are more familiar with those than I am, and I do not intend anyway to do a survey. I will mention as we go along the work of Johari and Tsilikis, because it's been very, very important in opening my eyes to the problem, and also because in that work, I mean, Johari and Tsilikis and the third co-author called Malou, I think, they actually specifically look at a cost-sharing issue of the sort I'm dealing with here. So that's why there is some really direct connection. Okay. All right. So in the result I'm presenting, I'm going to be making a pitch for serial cost sharing, which is a specific cost sharing method which I've been working with on for a long time, and following the initial impulse of Scott Schenker, and so that's going to be one conclusion. But the more important thing I would like you to take from this talk, if possible, is some interesting open questions. I mean, it's really a paper in which I'm more excited by the open question than by the ones that are closed, in a sense. So, all right, so let's start with a few examples motivating the paper, the model, because the model will be very dry and mathematical, but I want to try to take a few minutes to convince you that this simple model of production externalities, which is this simple, one input, one output model I'm going to discuss, is really very central to mechanism design. I mean, it's one, the model is going to be like this. I mean, there will be one technology to transform one input into one output. Each input and output will be divisible, right? So they will come in divisible quantities, which of course is not a fundamental restrictions, but one which makes computations easy and so forth. And that technology has decreasing returns. Decreasing returns meaning that if it's viewed as a cost function, the marginal cost is increasing. If it's viewed as a production function, the marginal productivity is decreasing. Okay? Now, this is the traditional setup of the so-called tragedy of the commons when you think of this input as being labor, the labor produced, supplied by a bunch of workers or people involved in utilizing those commons, and the output is whatever the commons produce. I mean, so in the standard, very standard economic parlance, I mean, when we speak of how to manage a commons, we have in mind this basic example where the technology would represent a lake or a forest or a pasture. And if it's a lake, I mean, the input will be the amount of labor that the fishermen, the various fishermen put into the lake, and the output is the amount of fish that they catch as a result. And the decreasing return character is, of course, central because this is the one which means that essentially this is an exhaustible resources. And if you're, and of course, as a result, an observation that goes back to even way before Adam Smith is that when this type of command is selfishly managed by people simply deciding independently how much work they put into the lake, then there is overproduction. There is over-exhaustion of the resources in a sense that we make precise by saying that we dissipate a great part, sometimes all of the available surplus. Okay, so that's the very fundamental paradigm of the tragedy of the common, which is in this output, what I call this output sharing game, because here the strategy is how much input you put in, and as a result you get a share of the output. Okay, now another you can also look at the same sort of this first, if you want, I mean this first model of labor give me output, that would be a model of a cooperative production. I mean, you can think of those fishermen who own the lake in common as the cooperative of production, and the issue is how should they split the result of their efforts in order to bring a more efficient management. You can also look at the same sort of problems backward as a cost-sharing issue in which you have a sort of a buyer's cooperative, where the issue is that we need to procure certain amounts of a desirable output, I mean some services and so forth, and these services are supplied by the competitive market. So what happens is that, and we are jointly deciding how to get our supplies of this commodity, of this input. So in that case, again, my strategy will be to require a certain amount of output, given this total output, we're going to go on the market and get it supplied. But with a typical competitive market, we know that the more output we demand, the higher will be the price we will have to pay for it. And therefore, you have your decreasing returns as before, the same sort of basic feature of the technology. And fundamentally the same problem, but in reverse, where your strategy is how much output you want, and your payment is what the mechanism tells you is how much you pay. Now, in the context of games played on the internet, network games, which in particular apply to the internet, but more generally to queuing, scheduling problems, I would argue that more often we see, what I've seen in the literature more often are of the output cost-sharing game, where the strategy is how much service you demand, and what you pay, your cost share, corresponds typically to a delay. In one of the most classic model, which is the initial game that Scott Schenker designed, what happens? Here we have a game in which, so it's really just a queuing problem, right? Where each particular user, there is a single server who is a standard Poisson server, and each particular user sends a flow of jobs at a certain rate, which he or she controls. You control the amount of bits that you send for the server to process. Now, given all of the requests of the various users, the total, the per unit expected delay in this Poisson system is well known, easy to compute, and it's of the order of 1 over lambda minus sum of the x. 1 over the difference between the rate of service of the server minus the total rate of the demand. So that is right there your cost function and your increasing marginal cost technology. And it's really, that game is really an output sharing game where you demand a certain amount of service and you pay, this time not in money but in delay. Okay? Sometimes, of course, if you now go to another type of congestion games, like the ones discussed by Kelly, Johari and company, then often the idea would be I demand a certain amount of the commodity, which could be bandwidth or it could be a certain flow of service, and then I get to pay some kind of fee which is going to be designed to create the right incentives and bring about efficiency. So in that case, the input could be money instead of delay. Okay? Yes, you had
a game we call here 520.
I don't know what's 520.
It's a badly traffic jammed highway.
Okay.
Try to get on it anyway.
Yes. You mean at 520 if you go on the highway.
No,
right.
It's a road number, but
right.
It's a route number of,
right.
of a particularly badly congested highway.
Right.
That's particularly badly congested at 520.
Exactly.
And in all other hours.
And in all other hours.
Yes.
I go home at midnight.
Okay.
Right. No, that's okay. So here so then I could go on and of course and describe a bunch of other cost-sharing games. But you see the idea. The idea is you demand a certain job size, and then based on the constraints of the server, you have a certain cost to share, which could be delay, which could be money, but it's always the same structure with this convex technology. So that's the motivation for. And now what I'm going to do is present the model in the cost-sharing form and tell you a few things about the output sharing form at the end. So here really what we can keep in mind is there will be this cost function like this. So here will be the xi that will be the output, and yi here will be the input for my. So I demand certain amount of output and I get to pay. But we can look at it. The output sharing would be to look different the other way. All right. So I want to apply the idea of price of anarchy, which is simply to try to evaluate the worst case scenario as far as the loss of surplus incurred in the strategic equilibrium of the game. Now, why is that idea so good, so convenient for this kind of problems? Well, first of all, by looking at a worst-case scenario, the great and worst-case scenario over all possible Nash equilibrium of a game, the great advantage is that you completely bypass the difficulty and the messy difficulty of equilibrium selection. Because by hypothesis, you sort of say, look, I mean, I don't want to say anything specific about which kind of equilibrium would emerge. I mean, I know that, you know, all of the standard refinements are all refinements of the Nash equilibrium. So I just take the worst situation at any Nash equilibrium ever, which is a very nice way to sort of sweep around the rug all the very messy subtleties of different types of equilibrium and which ones are more plausible. I mean, that's already a good thing. And the other thing, of course, is that by doing so and getting into a single index, a single performance index, then you're going to have a complete ordering of your mechanism. I mean, you're not going to have things that are non-comparable. Now, there is another trick. There is another trick which really plays a central role to make the analysis tractable, and that's the linearity lemma, on which I will come in a minute. So that will be in a slide or two. Okay, so here are my assumptions. My cost function C. No problem. Now, here is the central object. The central object of the theory is really these mechanisms. This is really the class of mechanisms that I am sort of allowing us to consider, right? So, of course, at this stage, you should pause in any mechanism design approach. You should pause and be sure that you like what you see there before going on, because everything depends on it, of course. So a cost-sharing mechanism will be this mapping from, if I have n people and a cost function which are given, so that they are supposed to be given, and now it tells me for any profile of demands, what should be the cost shares. For any profile of demand, so X is the profile of demands. Everybody is demanding a certain amount of service. Y is the profile of cost shares, which is what they have to pay in money, waiting time, or whatever. Now you notice that, so Y sub n simply means the sum of the Yi. You notice that I'm not requiring here equality. I'm not requiring here equality. Why is that? Because sometimes, I mean, some of the mechanisms you can think of, and I will give examples, are in fact some of the mechanisms which are the most interesting do not have this budget balance here, do have a strict inequality. And here I'm thinking of, in particular, I mean, the incremental mechanism that we will look at in a minute, in which you can guarantee that the efficient quantity is produced in equilibrium, but you pay a little too much. Very much like, if you wish, Vickray-Clark-Groves mechanism, in which you guarantee efficiency, but you have some budget surplus. Okay. So I will, of course, insist on budget surplus, not the other way around, because we are talking of feasible things which can be truly implemented without borrowing from an imaginary banker, right? But also an important thing, a very important thing, for those of you who know a bit this literature, is that I will depart from these papers by Joharit Silikis and Bruce Hayek and his co-authors and a few others, who have the following problem, in my opinion. I mean, they do look at mechanisms in which, indeed, you cover typically more than the real cost, but they then forget about the budget surplus in their accounting of the equilibrium surplus. In other words, they work as if this money that was paid in excess of the actual cost was able to come back through the back door and be enjoyed by everybody in the economy. So I find this to be either a cheap trick or a naive assumption. I mean, one or the other, but I don't think it's really acceptable here, because you see, I mean, we know very much from things like the VCG mechanism, I mean, that we can implement a very strong degree of strategic robustness, I mean the dominant strategy, but at a certain cost, and the notion that this extra budget, it will be transferred to the state budget, which later on will of course give it back to us without any distortion in the form of goodies and so on. I mean it's totally irrelevant and wrong. I mean in the sense that here, at least, let me say this. I mean, it's at least wrong if we think of this as a cooperative venture of users who have to decide jointly and together what kind of mechanism they will set up to manage their relationship in the future as far as this commons is concerned. So because these people are concerned by their accounting, they're going to have to pay a rent to the manager. There will be some extra money that should be taken away from them if the incentives are to be right. So, okay, so we do take that into account. And as a result, of course, for the same mechanism that they study, the conclusions are a lot more pessimistic here because, when you take this into account, things change. Okay. The symmetry here is not really essential. It's just that I'm only looking at symmetric examples, so it's not too much of a restriction for these particular computations in the paper. Now, here is a two very important assumptions, but the first one more than the second. The fact that the cost share, my cost share as a function of my own strategy, of my own demand, is increasing. That's sort of clear, but convex, that's very crucial here. Very, very crucial, because it's this convexity which guarantees that no matter, which guarantees that with standard economic preferences, you will have existence of a Nash equilibrium in every game. If you did not have this assumption, if the yi could be anywhere non-convex, you could easily construct examples of utility profiles in which the game has no Nash equilibrium, and then the whole exercise is put in jeopardy. I mean, you could of course say, okay, I could invoke a mixed strategy and equilibrium there, but they are completely untractable, in this with continuum of strategies like this. I mean, forget it. I mean, it's going to be horrible to compute mixed strategy equilibrium, and also it. My sense is that then, if you are talking of worst case scenario thing, and you are not even able to guarantee existence of an equilibrium. In other words, you sort of can predict that the things could cycle forever along a very complicated path. Then the worst situation that could arise becomes even much worse because it can wander around everywhere. So, you just have no control on anything. So, all right, so that's very crucial. The second one here, the fact that if I demand nothing, I pay nothing, it certainly is natural from a normative point of view, but it's actually not crucial here. It's not crucial because you can easily see that if that assumption was not satisfied, you can think of a very simple mechanism like equal split. Equal split is not such a stupid mechanism. In real life, we see it a lot, even when people have very different demands, when they decide, for the sake of not having to worry about anything, to just have equal split. That's a mechanism which violates that somebody who demands zero pays nothing, because a lot of the services that are provided by the states, you could say are equal split, because we all pay for subsidies to transportation, opera, football stadium, whether or not we use it zero or a lot, etc. So you could say it's an important class of mechanism, but if you have positive cost for some zero charge, then it's easy to see that there are Nash equilibria in which the surplus is negative. Because somebody is forced to pay who hates it, and the others are asking some service, and that's their equilibrium, but they get almost no surplus. So therefore, the price of anarchy here is infinite. You see what I'm saying? There is no point. You cannot even look for a positive share of surplus left if somebody who demands nothing is charged. So in fact, it is not a restrictive assumption if we look for the best possible cost-sharing mechanism from the point of view of this index. Okay. Now, after, okay. Right, now some terminology, which is, that's fairly straightforward, but it's important to say it clearly because I think here, okay, in order to be able to do any of this computation, we're going to have to assume something which is very standard in a lot of the economic literature, which is so-called quasi-linearity assumption. I mean, there is no exercise if we have no way to measure everybody's utility in some single commodity called the numeraire, vis-à-vis which everybody's utility is linear. Because if we don't have this, if we have more general preferences, we can certainly study cost-sharing games, but we will not be able to measure, to have an intrinsic measure of surplus. Okay? So we have to have an assumption of that form. The alternative assumption, of course, in some contexts, it might make sense to have utility of the form xi minus vi of yi. That's perfectly possible. You know, if yi, remember yi is the share of input, perhaps it's your delay in this queuing game, and xi is the amount of service. So to say that your cost, the cost of your delay increase in a convex fashion, and you know you have a deadline, you just cannot wait for too long, makes perfect sense. And this is an alternative scenario which works. You can develop the theory under this alternative quasi-linear representation. It does give you different formulas. I have not done all the computations because it's kind of long, but I'm very convinced that the same general results hold. I mean, except that the formulas mathematically are a bit different. Okay. So now you talk. So you normalize the utility of 0 at 0. That's just a normalization, and your utility is concave and increasing. Now you can talk about the surplus at any particular demand profile for some utilities. That's the total utility. Oops, here I should have said, well, okay, no, sorry. That's the net surplus. That's good. Yeah, that's the net surplus when they just demand X and the utility is U and they pay the real cost. And therefore, the efficient surplus is the max of this quantity. Is the best you can extract in this economy if you are omniscient and are able to get your agents to reveal everything there is to know, and you can control them and tell them what to do. Okay, so the relative surplus gain at some profile X and the utility U will be this ratio. Okay. So now, oops, I have to define my games and stuff. Okay. Yeah. I see that I have a little typo. Okay. So now I have my demand game, which is defined once I know what is my cost-sharing method and what is my utility profile. Right? I need to know both to have a game, and that's the game which is listed here. So it's the game in which I choose how much output I demand. Everybody else independently makes his choice based on my utility UI. And then I get the utility UI xi minus yi, where yi is my cost share as described by the mechanism. So the only interaction I have with the others is that the fact that they demand more or less affects my own cost share, and that's where the interdependency is. Okay? So now I can talk about the Nash equilibrium set of that game, and with the assumption I made, most critically, the assumption that my cost share depends in a convex fashion upon my own demand, I guarantee that this set is non-empty. Okay? And now I talk, and here you see I have a little, well, I should correct this a bit, because here I do as if in the X, which is a Nash equilibrium of the game, I do as if they are paying real cost. So I do exactly the mistake that I was saying, I was attributing to Johari. Here, what I mean in this expression, I mean that they are counting their surplus with the real cost that they are paying, which could be more than the actual cost. So I should rephrase this formula so that here we know that it's the sigma ui xi minus what they actually pay, which could be more than the cost. And then you divide that by the efficient surplus, and you take the minimum over all Nash equilibria. Okay? And I call this ratio, I call it guaranteed surplus gain. Okay, infimum of, and the infimum is over all profiles of utility. I mean, of this concave quasi-linear utility. So it's over all potential these functions UI. Okay? All right, so that's the number I'm interested in. And that's the problem. I would like to have this number as high as possible. And all right. So now here comes this key result. Simple observation, very simple, but completely central to the exercise, which is that when we do those computations of the worst case surplus loss in any Nash equilibrium of the game, we don't have to worry about using this complicated, concave utility function, UI. We can just assume that they are linear. It's not a very, it's a very, once you see it, in fact, I remember seeing it and saying, wow, I mean, that sounds right. And then, okay, it's not very difficult to prove once you know that it's there. Why is it so central is because now you see, when I have my cost function and my cost sharing method, when I want to start computation over all profile, I just have a list of n numbers. So now, of course, it becomes close to tractable, whereas before with n functions, you can see that the difference in magnitude of the complexity is enormous. I mean, so that's really is absolutely key to the exercise. I mean, and again, not very difficult. It's in the paper. I mean, it takes two, three arguments, but not much. Okay.
So the fact that you sort of said the sum of your, I mean that there may be some excess cost doesn't enter into that fact. No. It's completely general. I mean, yeah. It works also for output sharing game. I mean, it's a very yeah. So what does it rely on? Just on convexity? Or?
Yes. Yeah, absolutely. Okay.
I mean, you said, of course, it should be true. So, I mean.
No. It's a fair question. I mean, okay. So here, this is my input share and my output share. So this was the cost function. But now let me draw an arbitrary. Let's say this is my cost share, yi of xi. So I'm fixing the strategy of the other. I'm looking at my own cost share as a function of my own demand. And we just said it is convex, right? I mean, that's the key assumption. So in equilibrium, right. If this is my utility, the indifference curves of my utility function, you see that I want more input, but I want less input because the input is what I pay. So that's why my utilities are like this. And moreover, by convexity, they have this shape, right? I mean, they have this convexity. And in addition, since they are quasi-linear, they are also, you can translate them to go. Okay, fine. So this is your equilibrium. This is your, let's say that this is in equilibrium. So that's the equilibrium property, right? I mean, so now you replace this utility by this other utility, small ui, and you see that you still have the equilibrium property, right? So it's still a Nash equilibrium. And now you must evaluate in the computation of surplus at the equilibrium versus surplus versus efficient surplus, what's the difference? How much you affected the equilibrium surplus and the efficient surplus. And the equilibrium surplus, you affected it by what? By what quantity? I mean, if I draw, the thing is I have to draw my UI starting at UI equals 0, or if you wish, I can do it like this. If I draw it here, with the normalization here, what I'm losing is essentially this, right? I mean, in other words, when I do my computation of the surplus, which in the numerator, which was ui xi minus yi, now I replace that by small ui xi minus yi. Well, the difference is really the difference between this linear function ui and the concave ui, and it is achieved here, and it's the maximum of this difference over all xi. You see? Because of the tangency. So, which means that in the numerator, you're going to be taking away these quantities, and in the denominator, which is the surplus, you're going to be taking away less. So you have all the right inequalities. So it's really basic convexity stuff. Very, very basic and nothing fancy. Okay? So, but it really then make your life livable as far as trying to get some general results. So general results I wish I had, I really would be happy with, but unfortunately, as you will see at the end, all I am able to put is some very nice, I think very nice open questions. And I already spent quite a bit of time finding out what the situation was as far as this price of anarchy for 4 methods of importance, because they are in some sense the 4 most central method discussed in the literature. And here is what I'm going to explain. So these 4 methods, of course, here there are only 3. There are only 3. The last one will be serial cost sharing. But the reason I put these 3 first is that they have some similarity and they stand out rather different from serial. So the first one, of course, average cost pricing is by far the most important, because this is you can defend it in a million ways, in particular normative ways, as being the sort of the most straightforward interpretation of fairness in this context. It's the easiest to. Most importantly about average cost pricing is the fact that under average cost pricing, transferring demands across agents is of no consequence. So therefore, and it's the only method which has this kind of property. I mean, if I transfer you some, well, actually marginal cost pricing also has it, but among those which are budget balanced, I mean, if I transfer some of my demand to you and I just ask, you are charged something, and then we make a deal and I repay you something, I will not, that will not change the total of our 2 cost shares. Yes?
Is that what the Canadians refer to as blended price when they were selling oil in a bad market? You haven't read that?
No, blended.
Blended, they call it blended price. Some imported oil was horrendously expensive and some oil from Canada was cheap, and they blended the prices and sold them at some
Probably,
prices.
yeah, it must be something like that. I mean, yeah. Okay. So marginal cost pricing is also often discussed, in particular in this work of Tsilikis and so forth. But in fact, here it's because I'm going to take into account its excess budget. I mean, you see, marginal cost pricing pays too much. And if you look at this inequality, the share under average cost pricing is always less than the share under marginal cost pricing, and average cost pricing covers the cost exactly. So marginal cost pricing pays too much. And similarly, in between, you have incremental cost sharing, where you pay your incremental cost, which has the advantage that in the Nash equilibrium of that one, you are always efficient. You get, because the derivative of this margin of your cost share is exactly the marginal cost at the total level. So the only in any Nash equilibrium of this game, you produce the efficient quantity, but you pay too much, so you get a surplus loss from that. But then there is these inequalities. Okay. And surplus serial cost sharing is a completely different formula. Which is a bit of a pain to.
I understood the incremental. What was the marginal cost sharing?
Oh, marginal cost pricing was simply you pay at the marginal cost in the total production. So if the total demand is xn, we take the marginal cost at the total demand, and that's the price we charge to everybody.
Okay. It's not. I mean, it's often discussed. I mean, but it's not.
Marginal sort of. So marginal is
Because you pay marginal cost.
That's incremental in the total and not incremental in me.
Right, right. Marginal cost means that it's the derivative of the cost versus incremental cost, like an increment from with me and without me.
Just the first.
Yeah. It's those terms are rather standard in the cost-sharing type literature. Yes.
And you'd think if it's a big market of small customers, then the two bottom would be always identical.
Yes.
If everybody's very little, then marginal essentially it's difference calculus versus differential calculus.
Absolutely. Yes. Okay. So serial cost sharing is completely different in terms of its logic, and the formula is a little bit. I mean, it's there. It's a little bit of a pain, but for those of you who haven't seen it, I mean, I think it's much easier to explain it like this, like inductively. So you have C, and you have your demands x1, x2, xn, and the key, of course, is that you have to arrange them increasingly. You are paying attention to the order statistics of your demand, so you pay attention to who has the smallest demand, who has the next, and so forth. Given that, you're going to charge to the first agent as if everybody else was asking like him. So the definition of the method can be summarized in two sentences. One, that it treats everybody symmetrically, and two, that your cost share does not depend upon upon demands of people with higher demand than yourself. So if you look at x1 and you change all the x2, xn into x1, that is not affecting his cost share. Therefore, if everybody is demanding x1 by symmetry, he must pay C of nx1 divided by n, and that's what he pays. Now, for the second person, remember x1, x2, and then the other x3, etc. So the cost share of the second person does not depend on higher demands x3, x4, xn, as long as they remain higher. So therefore, you can lower them down to all x2, x2. And what you do is then you have to share equally between n-1 agents the cost from Cnx1. I mean, so you have to pay first of all y1, which is whatever you paid for the first part, plus 1 over n-1 of the cost between C of nx1 over here, and here C of x1 plus n-1 times x2. The increment going from everybody demanding x1 to the first one staying at x1 and everybody else going up to x2, that much is divided equally among all people 2 and above. And then going from cx1 plus n-1x2 to C of x1 plus x2 plus n-2 x3, going from here to here, we'll share the incremental cost equally among these n-2 people and so on. So it's this little algorithm, very simple to understand, and when you develop it, you get this formula, which is a little bit ugly, but okay.
Are there natural examples where the serial cost sharing is applied?
Well, yes, I can give you some. I can give you some reference, for instance, of some guy who was asking farmers in Montana or Wyoming how they share the cost of maintaining ditches. Watering, irrigation ditches, and the issue there is, how do you maintain? I mean, do you share globally by the volume that you get, or you go incrementally? So, I mean, I can give you some references, and I mean,
that seems very fair, right?
Well, it's a different sort of fairness. I mean, it's not a. Yeah, I mean, there is a literature.
Rich.
You had it?
Yeah.
It may not be an exact match, but this is remarkably similar to Maimonides' rules about dividing up a bankrupt estate.
Yes. Well, it's very. There is a lot of similarity in there because yes. Also, there is in game theory this thing called the airport landing game of Owen and Little Child, where you have to divide the cost of this long runway, and some company use planes which use the whole runway, then another company needs only that much of the runway and so forth. So you need, or you need to divide the cost of an elevator, so people who are in the first floor, they share, everybody share the price of the first floor elevator, then only the second and up. Those things, and those things are used in practice. I mean, it's a simple, but mostly.
We have people here who actually have elevator problems.
Okay. So I can give them a consultation on this. So initially, when this formula came up, I mean, in Schenker's work, I worked with him on the strategic properties of the method. They are really, its strategic properties are unique in the following sense. I mean, no matter which preferences you use in this game, and in particular, without assuming quasi-linearity, much more general, convex ordinal preferences, which are convex and monotone and continuous, you can always guarantee with using that cost-sharing game that the Nash equilibrium is unique Nash equilibrium. And moreover, it is a super strong type of equilibrium. It's called a strong equilibrium. It's a Stackelberg equilibrium for any, in coalitional sense. I mean, Scott and Eric Friedman, they have also another justification as the so-called overwhelming elimination of overwhelming. I mean, there are many angles in which, it's a game in which this equilibrium, the Nash equilibrium is unique and very compelling. Whereas in all the other methods, and not just the ones I described, but any method in a fairly large class, you cannot expect to have this uniqueness of Nash. So it has this.
Wait, what if X2 says he gets in cahoots with X1 and says we share sort of the total cost? Is that stable against that?
Okay. When I say strong equilibrium, it's stable against coalition moves in which if 1 and 2 get in cahoot, they still have to consume y1 and y2 as the mechanism, as to pay y1 and y2 as the mechanism says. So in other words, I can say to you, please decrease your x1 and I will increase my x2. But unfortunately, to agent 1 who decreases x1, it's just going to decrease his y1 and his x1, but he's not going to get any transfer from me. So I'm precluding you from under the table doing some transfer of money, transfer of the cost shares. If you do that, then nothing is in equilibrium because your Nash equilibrium being inefficient, all the people together can always get in cahoot and do better. You see, if you allow in the coalition moves to redo the whole allocation process, then of course, no Nash equilibrium will be stable because, but here, as long as these input shares, cost shares are non-transferable. If you think of delay, for instance, and it's very difficult for me, to transfer my delay to you, then it is. I mean, if there is no money,
No,
right?
he transfers his delay to me all the time.
Yeah, I can see that. Right. But you need long interactions for that. I mean, So in that sense, I mean, it is very robust. I mean, but provided, you stick, whatever you consume is what the mechanism allocates to you. You cannot do transfers in addition to that. Okay, and then after that, I mean, there were a bunch of papers in which I've contributed heavily. I mean, probably too much on the, the fairness property of serial cost sharing. I mean,
None of this takes into account that sometimes it's cheaper to build a long runway than a short runway, right?
When is that?
No, that's not taken into account.
You ever
because the
bought
convex
land in a
cost
next
function-
town?
No, because sometimes it's actually, right, you have sort of, it's cheaper to produce higher quantities per quantity.
Well, you could
Yeah,
presumably do a modification of this, but it would become horrible,
It may be
right?
cheaper per
Because it's
yard
not
without
linear
that.
anymore.
You mean the
Not
convex,
cheaper,
the
but
C non-monotone?
Not convex, I think.
Non-convex.
The C non-convex? Well,
Interchange.
the C non-convex, you lose a lot of the strategic properties. Not really, you don't really lose the fairness properties.
Right.
But in this exercise that I'm doing today, it's a big problem because you don't have Nash equilibrium anymore at some profiles, and that's very.
Is serial cost sharing related to ordering people in some random order and charging them the incremental cost, or is it different?
It is in some model which involves, which I could explain after the talk. I mean, it's kind of, It is related, but the connection is a little bit long. I mean, it's through a model of random assignment, where so let me skip that and we can. Okay. All right. So now here I have a couple of slides which I will go on quickly to explain that these four mechanisms, if I choose certain utility profiles properly, I can guarantee that any one of them gets the highest surplus. So in other words, there is no systematic comparison of the surplus collected in any particular Nash equilibrium at any particular profile by these mechanisms. In other words, the fact that, for instance, in marginal cost pricing, we pay more systematically than in average cost pricing doesn't prevent the situation where for certain types of utility profiles, in equilibrium, marginal cost pricing is much better for everybody. And so on for all four methods. I mean, because there is no clear monotonicity like that. So for instance, just to quote two, but then I will go quick. One case where clearly serial wins is when you have unanimity, identity of utilities. That's always very good for serial. It systematically gives you full efficiency, whereas the others systematically will give you some inefficiencies. And also in the context of linear utilities, just linear utilities, if you have linear utilities that are all different, linear utility which, I mean, in fact, I only need the first one to be strictly bigger than the other, then incremental method is going to be first best because only the first person will produce. But remember, this is because of linear utilities. I mean, the first person produces at the efficient level, and then everybody else is shut out because in order to produce, the marginal cost that the first person is paying is exactly U1, and the marginal cost on his cost share, and therefore nobody else can enter, and that's it, and that's a perfectly efficient Nash equilibrium. But of course, that's not true. If the UI now are not linear but general concave, then the incremental is not particularly efficient, and so forth. So then I have other examples where sometimes ACP wins and MCP, but I'm going to skip those. They are not so important. Okay, so now to results. And the results are really to try to make a case which one of these methods is best from the point of view of price of anarchy. And I have, in some sense, three different results which cast a different light on this question. I believe that the last one is the most important, but so that's why I keep it for the last. And you will see that according to each view, it goes a bit different. So start by what I call universal guarantees. So in other words, here I'm looking for a bound on the guaranteed surplus gain, which is independent of the cost function. Independent of the cost function. So no matter what cost function C I have, it is a fact that under average cost pricing as under serial cost sharing, you have to have at least 1/n of the efficient surplus. And whereas for marginal cost pricing or incremental, this is not true at all. And to see that, you just take a two-piece linear, a linear cost function, cost function which is a two pieces linear and convex. And it's very easy to see that in that case, for those functions, marginal cost pricing and incremental guarantee nothing. So it's interesting to see that you can draw a conclusion completely irrespective of any specific technology. I mean, it's not that great of a ratio, but it's something, right? So, and one of the open problems I have is kind of obvious from this, is 1/n the best we can do? I have no idea how to address that problem. Sorry.
You mean 1/n for
if I choose
MC?
Right. If I choose another cost-sharing method psi, an arbitrary cost-sharing method psi, this number, and I compute the infimum over, I fix n and I compute the infimum over c of this number, I may get 0, I may get 1/n, I may get something even better. But I just cannot tell you, don't even have a hunch of whether or not it will be possible to guarantee more than 1 over n. I sort of sense that it may be the best, but it's just, just a very naive thing, because those two methods being so important, but that doesn't mean much. I mean, really not much. Huh? So, okay. So that's one first. So the proof of that is not very difficult, but for instance, let me show you for serial.
Can you show us why those are bad with the piecewise linear, why the marginal and the
Sure.
incremental are bad?
Sure. That's easy. It's
By the way, you can go till 3 o'clock.
Yeah, right. No, but I will be finished then. So if you take simply a cost function like this, two-piece linear, there is no loss of generality in starting by a 0 marginal cost. That's really no loss. So then 1. Okay. So now you have n. You have n people, and you take. Right. You take them all at 1. Let me double check. You take them all at. Let's see. Right. Okay. Yeah. Right. Okay. So you take.
I mean, if it's
No. It's very simple. It's just that I did not remember the trick. I mean, u1 equal 1, and u2 equal un equal epsilon. Okay. So now the trick is this. In equilibrium, remember, in equilibrium of, let's say, incremental, you always produce the efficient quantity. And the efficient quantity here is obviously 1, because, this could be 1 minus epsilon, let's say, but it's because, up to here it's free, so we should take it. And after that, the marginal cost is 1, so there is no gain. But the optimal way to do that is to ask agent 1 to be the one consuming, right? For a surplus of 1. But in one equilibrium of incremental, what you have is that x2 equal xn equal 1 over n minus 1. Actually, you could even have just x2 equal 1, and x1 equals 0, and xi equals 0, or they all demand 1 over n1, and he demands nothing. So he's shut out like in a standard sort of battle of the sexes situation. They are preempting and consuming the whole free good, and leaving him with a marginal cost after that, which is too high, so he consumes nothing, and everything, all the surplus is lost. Whereas under serial, what happens is that they all get to share. I mean, all these small users get their share of the free goods, 1 over n, but even the good guy gets a share 1 over n. Because for the initial, the lowest cost, marginal cost, we share equally until some people drop off. So the good guy gets, so you do get that much. Okay? And for average cost, I mean, it's similar. I mean, you have to write the formula for average cost, but it works as well. Okay? So that's fun. I mean, but again, I mean, yeah, there is an open question there, which I cannot. Okay. So, all right. So now, what I did, I mean, not exactly in that order, of course, but in the way I present it is now, let's look at the way for a fixed cost function, and of course, the most natural cost function here will be those power functions. Let's take the power function, of course. And so this is taken so that the marginal cost is going to be exactly a to the p, right? And of course, I work all the time only with the marginal cost for the formulas. And then I get this mess. I mean, so don't try to, unless you are very good at figuring out how functions vary in terms of p. P, remember, is the degree of convexity or concavity. So for p, For p between 0 and 1, this is like a concave marginal cost. And the cost function is always convex, but the marginal cost can be either, this is the case of quadratic for the marginal cost. Then you have the case here, p between 0 and 1. So concave marginal cost, and then p bigger than 1, that's convex marginal cost. And this distinction will be central to the result now as well as the results that come next. Oops. Okay. So here is the figure. Here's the figure. Does this thing know how to turn around? No, not really. Eh? But I can.
Christian can turn it.
I can tell it to turn it off.
Okay. If it's not too much.
You're changing the light.
Maybe the guru in the back can do it.
No, but
Turn the projector around. Turn. Maybe what turn is turning. Thank you.
yeah,
Oh, it's done. Sorry.
yeah. Thanks. Then I will need you again to unturn later. But okay, so that's for p from 0 to 10. That's for p from 0 to 10, and you see a very different behavior of serial versus the other three, because for serial it decreases with p. So the more convex is your marginal cost, the worse for serial. Whereas for the other three, it increases. Okay, it starts at 0.3 over here, something like 0.3, and here very high, 82% or even 77% for ACP. And then now let's look at what happens when you go for even more longer to 100, and then it's very striking that you get ACP which remains essentially flat. I mean, for the price of anarchy for ACP varies between 77 and 83%, and essentially flat all the way. I mean, except in the beginning. Incremental actually starts very low but reaches full efficiency. I mean, reaches 100% when P is incredibly steep. And in fact, it is joined by MCP. That figure doesn't show it, but far away here, MCP. Sorry. MCP joins ACP. MCP joins ACP, not incremental. So it becomes not bad over there. And serial goes down to 0.5. And the limit of serial here is 0.5, so 50%.
This is with how many players?
This is two.
2 players.
2 players. Right. 2 players. So it's interesting because, in fact, serial doesn't look good at all. I mean, it's the best for p between 0 and 0.36, which is the very beginning when the marginal cost is very concave. It is the best, but not by much. And after that, I mean, you could say, after that, it's very clear that it's not the best, and ACP probably stands out like nicely here. So these were the formula for these cost functions, right? Yes. Let's turn it back. Thank you. Thank you. No, that's good.
Turn the light up.
A bit more light.
I can zoom in on
Yeah, we have to read every word.
The light is nicer.
Yeah.
Christian, but if he has more on his slide.
You're zooming,
That's fine.
More on the slide you want?
No, we don't care. But the light.
I don't think I
Stop.
touched the light.
No?
The underlight?
No, but that's fine. We are okay now.
It was lighter before.
This is even darker.
So go in the other
the other way.
direction, whatever you did. Just
It's kind of pretty. It has a kind of old-fashioned look,
Read it.
like a Woody Allen movie.
It's very
Okay.
Very good, very good.
Well, now back.
No, it's good. It's good. It's good. So it was for this power cost function, and I have this formula. I have them for, I mean, it's easy to generalize those formula for n with incremental ACP, MCP. I mean, I wrote them in the paper. For serial, it seems very hard. I mean, in fact, the estimation,
Wait, to generalize them in which case?
n to n. To n
players.
players. To n players, it's easy to get the formula and to draw them. I mean, I haven't done it, but the difficulty is to draw them for n. So I don't have, I mean, I will do it with the help of somebody good at those sort of things. But that's not too important because we can still say the key, we can still explain the asymptotic behavior slightly differently. I mean, in a slightly approximation, because here is the, in some sense, almost the main result. There is one case in which the serial computation is easy, and that's the case of quadratic cost, so p equal 1. So for p equal 1, namely linear marginal cost, it is possible to compute the actual surplus loss, the worst surplus loss of serial. And it turns out, and that's where, you know, all of a sudden I got a boost of confidence in serial again, because I see it now emerging as 1 over log of n versus 1 of n for 1 over n for all of the others.
Yeah, you mean 1 over
Something over n.
Yeah, I mean 4 over n, 2 over n. I mean, the connection between ACP and MCP over all power functions is always like that. That MCP is a fraction of ACP, and whereas serial is 1 over log of n. I mean, essentially, right? So that's very striking, and because it really means a great deal of difference in the asymptotic behavior of serial versus the other three. Yes.
The difference between MCP and inc going persisting to infinity looks strange, because you'd think that, you know, if all the players are small, then it doesn't matter whether you do the derivative or the divided, but it does. It's one is 2 over n, one is 1 over n.
Yes.
That's strange. When there's a million guys, you know, the difference between my concern with me and without me must be.
It's just, but it's no. The difference in the shares is not great, but the difference in the incentives is subsequent, because in the incentives of inc, you have your marginal, you know, your marginal cost dy dxi is simply c prime xn, but for the other it's c prime xn plus xi c double prime xn. So
and the double prime does it?
Yeah, well, you have this extra term because you are taking the derivative of xi c prime, so you have more push, and therefore this one underproduces. You see, MCP underproduces, incremental produces exactly right, and the other two overproduce. There is a kind of theorem that I think should be true, but in fact nobody has ever proved that in all these cost-sharing methods that I described, if they are budget balanced, in equilibrium, they must overproduce. That's an interesting one, which I have to prove someday, but I'm pretty sure that's true. Okay, but whereas MCP underproduces and incremental just right. And so in the end, I mean, okay, so that's for quadratic cost. So then the trick is, okay, can we say something more? I mean, is this superiority of serial, very strong superiority of serial in the asymptotic sense, is that stable to other cost function? So I cannot claim it for any cost function, but I can deal with two classes which are in fact fairly large, costs for which the marginal cost is convex, and costs for which the marginal cost is concave. So which is, you know, substantial classes. So what you find is when the marginal cost is concave, like this, remember this is something which will be helpful for serial and in fact detrimental. This is the small p in the first figure that we turned around. It's detrimental to ACP, MCP, etc., but helpful for serial. So in fact the they tend to go down. I mean, these are not exactly the same numbers because, it's not exactly that they go down from quadratic, but I get that. But for quadratic, for ACP, it's exactly the comparison with quadratic. So it gets less than quadratic, and the other gets more. So for sure, it's reinforced the superiority of serial. Now, when marginal cost is convex, you need to bound the rate at which it is convex, because otherwise you go to this, like in my figure with the power p, and for very large p, you get that incremental becomes the best. So you need to bound AC double prime over C prime, which means that it grows less fast than x to the p. And then you get these bounds which are, which confirm that for serial, the surplus, the guaranteed surplus goes to 0 as 1 over log n, and for the others it goes to 0 as 1 over n. I mean, so that's absolutely confirmed. In fact, it's not difficult to prove for any cost function that the surplus in ACP goes to 0 as 1 over n. So in that sense, I mean, that's okay. That's very partial result because it's just for this method, and I can conclude now with some open questions, which are the obvious open questions for this, and then one word on the output sharing. Open question. Well, and I have tried and tried. I mean, but. Yeah, the main one is the top one. I mean, the main one is the top one. Let's fix the number of players and the cost function. What cost-sharing method will give me the best guarantee over all cost-sharing methods? It's a difficult problem because, I mean, the family of cost-sharing method is parameterized by, even if you have n equal 2, by a function of 2 variables. And then what you need to do is maximize over this function of 2 variables the solution of an already complicated minimization problem. Because you have to, first, to compute the gamma, you have to minimize this ratio of these two quantities. And then, I mean, it's just, I don't know, I would be very interested in any suggestion on how to attack that. I don't even know if you can think of attacking this in some numerical way or anything. I mean, I'm completely at a loss.
Specific instances of cost functions where you know the answer? Like
no.
Ones that you considered in the last page?
No. In fact, when I try to attack this, I always look at n equal 2 and C quadratic, and I try to get my hand on, okay, what could be and I failed and failed. I mean, so to me, it's really some slightly unsurmountable at this point. But and in particular, I would like to understand at least that. I mean, if we cannot find exactly the optimal solution, perhaps we could at least estimate the asymptotic behavior of gamma star and C in n, and see if it is of the order 1 over log n or better. Maybe it doesn't even go to 0. I mean, for all I know, I mean, it's not impossible that this gamma star on n remain bounded away from 0. I sort of doubt it, but that's all I can say. Okay, and similarly, there is this issue of the best universal bound. I mean, you can also look at this and try to find this number. I mean, so
you're souping over what class?
Well, I don't think I can make the class much smaller. I mean, what I've been trying to do, for instance, is the following with the quadratic cost, which is a scale invariant. I mean, it's a homogeneous function. So I'm taking cost-sharing methods which are on top of this scale invariant. So when everybody multiply the demand by a factor, you multiply the shares. So which simplifies your life because then it's a function of one variable. Your unknown is a function of one variable. Even then, it seems very hard. I mean, because you have to have a lot of conditions on the derivatives of the function and then solve a complicated maximization. I don't know. I will keep trying. I will try to enroll some mathematicians. At Rice, I was successful for the first time in my life, 6 years ago, to interest some real mathematicians in solving problems with me. So I will try that again. That was it. Oh, it's Richard Stong, who is a combinatorial specialist, but he does a bunch of things, and he just likes to do little problems on the sides to keep in shape. So that's good. That's all we need is to find this kind of mathematician. So one word about the output sharing game. Two variants. Yeah, there is the variant of changing the input as numeraire and having the linearity in the other. There, I really believe computations probably will be a bit more tricky, but it should not make too much difference. Output sharing game is a bit of the same story. If for those of you who know that literature, in fact, the games that people like Johari, Tsilikis, and so forth use are of the following sort. So there is this output, it's a congestion game, and what players do is they bid an amount of money, and based on this amount of money, they receive some share of output which is less, which total to less than the actual output share which is produced with the money that they put on the table. So it's an output sharing game of the sort where they receive less than what they actually produce. But apart from that, it's very similar to those games. It's very similar to MCP and incremental. It's somewhere in between. And the asymptotic properties, are pretty much the same, going to 0 as 1 over n. Once you take into account, of course, properly this surplus loss. So there, it's a little bit more work, but it's going to be a similar result. And here, finally, I think that there is probably something to say about an alternative interpretation of the adversaries' strategies in this game, which is to say that instead of choosing, for any n and any c exactly the worst method, we could assume, as a sort of simplification of minimization of his strategic possibilities of the adversary, that he has to choose a probability distribution over utilities, and for any specification of the size of the population, draw NIID members of that population. And then we could look at what happens when n grows large, and I suspect that in that case, methods like serial cost sharing will keep a positive fraction of the surplus in the limit. Because as soon as you force some regularity on the distribution of types across population, in a sense, the bad counterexample that make the serial cost sharing share go to 0 disappear, and so I think this would be a possible way, but also pretty difficult computationally to generate some more positive results. All right.
Here the rest of